Good morning. Today we see about time varying electromagnetic fields. So here we know electric field and static field. Electric field and magnetic field. What is meant by static electric field and what is meant by static magnetic field. Today we see about dynamic electric and magnetic fields. That is the electric fields and magnetic fields are varying with respect to time. If suppose electric field is varying with respect to time means what happened, and magnetic field can be varying with respect to time means what happened. That is the dynamics of electromagnetic fields. So the Maxwell is one of the scientists. He's developed the 4 equations. That equations are called Maxwell's equations based on the time varying electric and magnetic fields. So here introduction about time varying fields. So here electric field can be varying with respect to time means it can be produces magnetic field, and magnetic field can be varying with respect to time means it can be produces electric field. So the electric field and magnetic fields are interrelated to each other, and it can be produces one waves. That waves are called electromagnetic waves. That waves is carrying an energy and information. So applications of these electromagnetic waves are generation and transmission of AC power, transformers, motors, generators, and also in wireless communication systems also the waves are used. We know radio, TV signals, mobile, Wi-Fi, all are the examples for EM signals, radar and microwave systems. So first we have to see what is meant by electromagnetic induction. So the Faradays are developing the law that is called Faraday's law based on the electromagnetic induction. So here we have to take that electric time varying magnetic field. We have to take that magnetic field that can be varying with respect to time. So it produces something that it produces electromagnetic force EMF, so which causes a current in the closed circuits. So what is the Faraday's law means? Time varying magnetic field is produces the electromagnetic force, so which causes a current in the circuit. So it mathematically it can be written as V is equal to minus d phi by dt. So here suppose n number of turns are connected into the circuit, the electromotive force EMF is equal to minus n into d phi by dt. So here minus sign is indicates that the direction of the force is opposite to the change of flux linking in the magnetic flux. So this is a Faraday's law. So based on the principle of Faraday's law, we have to derive the 4 Maxwell's equations. So here electromotive force, 2 types of electromotive force here we can consider. One is a transformer EMF, another one is a motional EMF. And in a transformer EMF, the electromotive force V is equal to, you know, from the electric field, V is equal to line integral of E dot dl. According to the Gauss law, we have to consider the magnetic flux. So the magnetic flux around the closed surface, we know phi is equal to surface integral of B dot ds. So we have to take these 2 equations. Already you know that electromotive force V is equal to minus d phi by dt. So here instead of phi, you have to substitute d by surface integral of B dot ds. Okay, instead of phi, you have to substitute B dot ds. B is nothing but magnetic flux density. So it can be written as minus surface integral of dou b by dou t into ds. So already you know that related to electric field, motive force is equal to line integral of E dot dl. You can compare both equation. Line integral of E dot dl is equal to surface integral of dou b by dou t into ts. You know that Stokes theorem. You can apply the Stokes theorem here. So we can get, instead of line integral of E dot dl, we can write in a surface integral of del cross E into ds. So line integral of any vector is equal to surface integral of curl of that particular vector. So we have to take surface, instead of line integral of E dot dl, we have to write surface integral of del cross E into ds. So you have to compare both equations. We have to eliminate the common terms. Both sides we are having surface integral. So we can get del cross E is equal to minus dou b by dou t. So this is a point form of Faraday's law. So based on this Faraday's law, we have to derive the 1 Maxwell's equations. Okay. So next one is the motional EMF. So the motional EMF is based on the conductor moving. Let us consider the conductor moving in a steady magnetic field shown in the figure. So if a charge is developed, moves in a magnetic field, so it, because of that movement of that charges, it experiences the force. The force can be written as F is equal to Q, charge into the direction, velocity into magnetic flux density. Force to the charge can be written as velocity cross product with magnetic flux density. You know that force per charge is equal to electric field. So electric field is equal to V cross B. So here this is if the moving conductor in a closed circuit is generate the electromotive force around that circuits whose the direction is V cross B vector into dl. So this EMF is called as motional EMF. This EMF is called as a motional EMF. So here this EMF is can be varied with respect to the movement of the charge. So this is a motional EMF. So next we have to derive the conduction current density. So based on the Ohm's law, we know the current is equal to voltage to the resistance. So the here the current we can consider as conduction current, current around the any conductor. So it can be considered as conduction current. Conduction current is equal to V by R. You know that resistance value rho L by A. So here 1 by rho is equal to sigma. So we have to take as a rho is equal to 1 by sigma. You can substitute here. Substitute the R value to the conduction current. So we can get V sigma A by L. So we know that the charge is equal to E dot dl. So Ic is equal to, we can substitute this current to the area. So we can get Ic by A is equal to E sigma, that is equal to conduction current density. Conduction current to the area is called conduction current density, that is denoted a letter Jc. Jc is equal to sigma E. So similarly for displacement current, rate of change of charge enclosed in the circuit. Based on the rate of change of charge enclosed in the circuit, we have to calculate the current. That current we can consider as conduction current. So conduction current is equal to dq by dt, that is equal to C into dV by dt. Related to the capacitor, the charge can be written as Q is equal to C into V. So you can substitute here. So we can get Id is equal to sigma A d divided into dV by dt. So you can substitute sigma A d into, we know that V is equal to E into D. So substitute this value here and we write the conduction current density. Conduction current density is equal to conduction current to the area. So we can get Jd is equal to dou D by dou T. So these are the basic introductions about EMF and transformer EMF and motional EMF. From that one, how to get the conduction current density and displacement current density. So next we see about Maxwell's equation. So that is we see the next class.